regarding to the last statement for the cooling curve. Okay. All right. For this temperature, it is supposed to about 225 degrees Celsius. Why? Because if we talk about the end of solid formation, okay, for this point, just a second. Okay, so for this point, okay, this temperature 225 degrees Celsius is related to the point where the solids stop to form, or the point where the liquid completely transform into the solid. Okay. Sorry, saya punya pen ni dah habis bateri dah. Okay, ada. Right. So this temperature is actually the temperature at this point. Okay. This point is a fall on the solidus line. Okay. This is a solidus limit. Mean the limit where when upon heating, it's the beginning of formation of liquid, transformation from solid to liquid, or upon cooling, during cooling process, is the point where the solid completely form, or the liquid completely transform into solid. Okay, and similar to the other example. Okay, where is it? For this point, yes, this point. Okay, for this point, it is a 135 is supposed to about 180. Okay, this is 180. Okay, so means it is the curve. This curve shows the mixing between liquid and solid, which is beta. And during the changes from beta into beta plus alpha, it shows a constant gradient. Not really constant, means that there's no different in terms of the slope for the cooling curve. All right. Okay. So the microstructure. Okay. Okay. Next is last time we stopped at this point where this is the explanation of phase transformation for the alloy contain the complete beta solid solution composition as the primary solid. Okay, where the composition of this alloy, okay, the stannum composition is larger than 80%, about 80% of stannum. Okay, so if your alloy contain more than 80% of alloy, this microstructure you should obtain at this point. Okay, the deadline for this short assignment 2 is yesterday. Okay, however, you are allowed to submit up until 29th of April. I already extended the deadline, not extended the deadline, I allowed the late submission for this short assignment. Okay, next is this is the microstructure of complete solid solution of alloy for bismuth stannum. All right, so if you look at this microstructure, okay, the large grain like this is the primary beta. Why? Because during the because when we solidify a metal if the grain or nucleus form inside the molten materials, okay, this nucleus will grow larger and they will meet at the grain boundary. So the large grain basically is the first solid to form, which is primary beta. Okay, and it's grow larger until this, and it's completely form beta phase. And when it enters this region, there are another phase will form, which is alpha. Okay, originally it is only one single phase, which is beta. When it's the temperature cools below these limits, okay, what happened for this alloy is there are two phases will form, and the new phase is known as beta, alpha. Okay, so where alpha will form, it will form at the grain boundary. Okay, because it's this region is contain a lot of voids, so the diffusion will easily occur at this point, and the atomic arrangement for two element, which is between in this example bismuth and stannum, the diffusion and the concentration between bismuth and stannum will change um, primarily at the grain boundary. And what happens, the composition between bismuth and stannum will change from beta to alpha at the grain boundary. All right. Okay. So next is uh, how to determine that phase composition. Okay, so let's say we have at any point, okay, this is similar to the complete solubility example. For the complete solubility phase diagram, it shows a complete solubility like this: liquid, liquid plus alpha and alpha, from 0 to 100% of element B if we add into element A. Okay, so this is the weight percentage of um, element B. All right, because B is 100% at this point, A and 100% at this point. All right, in this example last time, we can determine the phase composition uh, by drawing the tie line like this. Okay, this tie line. All right, similar to this example, let's say we want to examine the phase composition at this point, we just draw the tie line. So in this example, if we draw a tie line at any point, let's say we want to analyze at 150 degrees Celsius temperature. So we can do that similar to the previous system. Okay. So for example, like if we want to determine the phase composition at 150 degrees Celsius for this alloy. Okay. So first we need to identify what is the phases uh, present at this temperature. Okay, our alloy is 70% stannum inside bismuth. Okay, and for this case, bismuth 30% and 70% stannum. All right, at this for this alloy, okay, let's say you have this alloy, and then you have it melted, and you want to solidify it. Okay, and during the cooling process, all right, you want to check what is the phase um, obtained at this temperature. Okay, the answer is liquid and solid, and you want to determine the composition. Composition means when we talk about composition, okay, it is a C. We write as Cl for liquid and a C beta for the solid beta phase. Okay, we want to know inside this liquid how many percent of stannum and how many percent of bismuth. Okay, so this is composition. And for the solid beta, we want to determine what is the composition of stannum inside this beta and what is the composition of bismuth inside this beta. This is what meant by composition. All right. So if we know the percentage of bismuth and stannum, we know the properties of this kind of your alloy at this temperature. Okay. So there's so many. This information is very important, especially when it relates with how material behave, react with the environment at this particular condition, meaning that it is not fully completely solid. And then you do the process, you know that inside there are several, the liquid phase contain a certain percentage of sand, so you can control the environment during the process. So this kind of information needed, okay, when you really practice this knowledge for the engineering application. All right, so now let's go back to the determination of the composition. Okay, for example, you want to determine at 150 degrees Celsius here for your alloy. So what is the composition of liquid? Basically, we write as Cl. So liquid phase consists of 49% stannium. How? Okay, so you draw the tie line like this, and then the intercept between the tie line and the liquidus line. This is liquidus line, and this is solidus line. Okay, right. So the intercept here is a Cl. Okay, let's say you don't know what is a liquidus, solidus. You don't want to memorize it. Okay, never mind. But the thing is, when we draw a tie line, okay, when we draw a tie line, uh, the boundary between the tie line and the neighboring face, you need to identify first. Okay, for example, like this intercept happen to the next phase, which is liquid. So automatically this reading is belong to the composition of liquid. And another point here, okay, point here is intersection between the tie line. Where's tie line? This is tie line. Okay, the tie line and the solidus line, or the boundary between the mixture and the beta phase. This. So automatically this one is for composition of beta. As simple as that. So now the Cl is 49% stannup. If your phase, liquid phase contain 49, mean the remaining is 51% is bismuth. Okay, again, your alloy, the total composition of your alloy is 70% stannup, but at this particular temperature, different phase contain different composition. Okay, so for example, at 150 degrees Celsius, the liquid at this temperature contain higher bismuth composition compared to the stannup. Okay, even though the total composition of alloy is 70% stannup, but at this particular temperature, you have liquid that the concentration of bismuth is higher. Okay, and then what about the solid beta phase? Okay, at this 150 degrees Celsius, the beta phase contain this, which is 83% of stannup. Okay, so remember, okay, stannup and bismuth, okay, it has different properties. So even though you already know that your alloy containing 70% stannup has a specific mechanical properties, but at this temperature, okay, your solid phase contain higher stannup composition. So this kind of information is very useful when yeah, you want to know the mechanical properties at this point and so forth. Okay, all right, so that's for the composition determination. Next is the phase fraction. Okay, so you know you have a liquid and solid here, okay, at this point, but they have a different composition. But you know, you want to know, if you want to know how many liquids remains. Okay, all right. Yeah, of course, you know that upon cooling, okay, as the temperature drop, okay, at this point, for example, it has a very small solid, which is beta, inside the liquid. And then at this point, the beta grow larger. All right. At this point, maybe 10% beta. Okay, at this point, maybe 30% is solid beta. All right. At this point, maybe higher, but how high? Okay, how many percent? You can determine. All right. Maybe it is a very useful for uh, okay, the application is maybe if you want to uh, to do some modification on the alloy. Let's say you want to add some doping materials. Okay, for example, the requirement is says that you cannot add this kind of element at high temperature because it will destroy the alloying element. For example, you want to put uh, inside your bismuth, you plus tandem, you want to add another X element. Okay, this require temperature 150 degrees Celsius. Higher than that, it will destroy this element. So you have to ensure by the time you add this X element, the temperature, the solid is formed, but it's require a small amount of liquid. For example, this is just example, okay? All right. So you have to ensure that, okay, at this point it's require, for example, 50% of liquid. So you want to check, okay, 50% of liquid at what temperature? Is it lower than 150 degrees Celsius or something like that? Okay. So this is kind of application where at that time you need to determine how many percent of liquids remain in your alloy during the solidification process. So just example. So meaning that, okay, the method is similar with the previous system, which is complete solubility system, where if you want to measure these elements, you need to measure the fraction of this length over the total length. Okay, so the opposite side. If you want to know how many percent of this element, you need to measure the fraction of the length at the opposite side over the total length. Okay, for example, here solid, okay, the length at the opposite side, okay, L, not B. A over the total length, which is A plus B. So the length is represent the composition here. Okay, the length inside the phase diagram, the tie line. Okay, so you can use this as the quantitative value to measure the lengths A and B. Okay, A and B. So B is here. B is located at the right side, and liquid is located at the left side. So if you want to measure beta, okay, which is a solid, okay, you take A over the total length. Okay, how to measure the length? By using the unit of uh, percentage stannum inside the alloy. Okay, for example, like this, the fraction of beta. Okay, how many percent of beta inside your alloy at temperature equal to 150 degrees Celsius. Okay, at this temperature, you want to know how many beta already formed. Okay, and then you calculate based on this. How you get A equal to 21 is coming from 70 minus 49. It is equal to 21 weight percentage of sternum. So you got 21 here. And then 21 over the total length. This one also you can calculate based on 83 minus, this is 83, the CS equal to 83 weight percentage of sternum. And this one is CL, which is equal to 49 weight percentage of sternum. Okay, right. And then we got this 61.76%. All right, and ml similar to the fraction of liquid. So liquid is on the left side, so you need to take the length on the opposite side, which is B. Okay, B, how we get B? B is 83 minus 70, so we got 30, 13, and over the total length, where we can measure 83 minus 49. Okay, CS minus CL. So we got the total length, right? And it is 38.24, or you can measure by 100 minus 61.76. Also, we got 38.24. So the percentage, okay, when we have solid and liquid, how many percent is liquid? How many percent of solid? Okay, let's say your process require uh, require a temperature uh, temperature. You want to determine what temperature that having 50% of liquid. Okay, you can use the same method. Okay, you can use the same method. Let's say if you want to add these elements, it requires 50% of liquid. Then only we can allow the absorption of the X third element. Okay, this is just example. There are many other purpose for this determination of fraction phases. Okay, so this is the example of phase diagram. If you want to do the soldering, okay, at what temperature it will produce a microstructure for the for example, if you want to do soldering, what temperature you want to use to melt your solder materials. Okay, what phases, whether you want it to be eutectic structure plus alpha, or you want it yeah, let's say if you have 100% eutectic structure, the melting temperature is lower than this one. Okay, to fully melt the solid of solder materials. Okay, so in a eutectic reaction, a liquid phase transform isothermally to two different solid phase upon cooling. So remember to determine this point, it consists of whether it is like this or like this isothermal reaction. So there are liquid alpha plus solid 1 or solid 2, or it can be solid 1 plus solid 2 transform into another no, this is not eutectic. Okay, this is another example of isothermal reaction, solid 3. Okay, so the point is, in eutectic you have this horizontal line inside the phase diagram and the V shape on top of it. Or another isothermal reaction, it have horizontal line like this and the V shape underneath the horizontal line, or maybe out above this line. Okay, it can be like this, S4 forming another S plus S. Okay, solid. So this is isothermal reaction, but for eutectic reaction, it is transformed from liquid into solid 1 plus solid 2 upon cooling. Okay, if you do heating process, so heating means solid 1 plus solid 2, it will transform into liquid. Okay, complete solid solubility for all composition does not exist. Instead, there is only a limited solubility. Complete solubility is a example like copper and nickel. Okay, copper and nickel, like water and alcohol, something like that. It will completely, but limited solubility is has a limit like sugar plus water. Okay, four different kind of microstructure that may develop for the equilibrium cooling for all belonging to eutectic system were discussed. Okay, the transformation during process from liquid to solid. Okay, I think that's all. Is there any question before we move to the next slide?
No.
Oh, laju je no eh. Okay, betul eh? Tak ada soalan?
No, doctor.
Memang ada doktor.
Okay, take a break at 5 minutes before we continue. project management, project. Welcome back, everyone. Are you still with me?
Yes, doctor.
Yes,
Yes,
doctor.
doctor.
Yes.
Very good, very good. Okay, regarding to the assignment, short assignment 3, you have to submit um, um, the assignment by Tuesday 27, and you have to check the similarity. Have you tried submit?
Yes.
Yeah, okay, good. All right. Yeah, from the instruction, a student asked me, um, uh, we need to prepare the answer in the one single A4. Where the yeah, because there are two different instructions. One is larger, more than 250 words. Another one is A4. Actually, uh, it can be both. Okay, but the most important, the words count is more than 250. And the reason I asked you to limit to one A4 paper because yeah, for the marking actually, uh, I afraid that I miss pages. Okay, if let's say you have more than one page, all right. I'm afraid that the there are some missing page. Okay, so if everyone submitted and I only found only one page, so I am more confident that you have submitted all the answer script. Okay, so if your words is so much, means that your answer is too long, so you can resize the font. Okay, resize the font. So the answer is you need to comply both requirement. Okay, so any question on that? Okay, it must be more than 250 words and limit to one page. Okay, so is everything clear now?
Yeah.
Yes, doctor.
Okay, good. All right. Okay, um, the last part for this module. Okay, um, binary alloy complex phase diagram. Okay, so in this complex phase diagram, you need to understand what it means by intermediate phases and compound. Understand the other isotomal reaction, which is eutectoid, paratectic, and peritectoid transformation. Okay, in the last slide, the lesson number 3, we talk about eutectic only, and that particular alloy um, uh, is is quite straightforward uh, for the isotomal reaction. Okay, meaning that liquid to solid, but there are more than that actually. Okay, and then the learning outcome number 3 is you should be able to interpret phase diagrams that contain intermediate phase and compound. Okay, iterative point is like this. Okay, you have a liquid phase. Okay, upon cooling, it transforms into solid phase. Okay, this structure we call it eutectic composition. Okay, only this alloy. All right, if you let's say this is a 50%, if you add 1%, you will get solid solution. Okay, plus the eutectic composition. And if you reduce the amount to 49%, so meaning that you got this phase containing eutectic plus um, alpha in the form of primary alpha. Okay, what is eutectic? Eutectic structure contain lamella of alpha plus beta. So there are both still alpha plus beta, but the structure of alpha and beta is different between hypo eutectic and hyper eutectic. Okay, so this is terminal phase for the one single phase of alpha. And this is also terminal pair that containing one single phase of beta. Okay, so the limits. Okay, you don't see this black line here because we can't determine this line at a lower temperature. Okay, let's say this is the okay, it is very complicated to explain, but just ignore this black line. Okay, all right. So the liquid phase. Okay, this is one example of complex phase diagram. All right. If you look at this diagram, it's contains sulfur up until 0.9, meaning that there are more if you add more sulfur inside. Remember, it is weight percentage. Okay, so the weight of sulfur compared to nickel, of course, very low. But imagine sulfur is do you know sulfur? Sulfur is like gas. Sulfur is very light element, very small, tiny elements. Okay, so 0.9 sulfur is quite huge as compared to nickel. So it is the number of atoms is quite huge, penetrated into the parent atoms of nickel. Okay, this is the terminal phases for the nickel, where the majority of nickel inside this region. This is terminal phase of this alloy system. Okay, at the far end between the left side and the right side. Okay, other solid solution. Okay, there are other solid solution like beta, delta. Okay, and there are intermetallic compound. Okay, the vertical line. This is intermetallic compound. This one, nickel 3 sulfur 2. This one, nickel 9 sulfur X. Okay, this green line, nickel sulfur. Okay, this magenta line, nickel 7 sulfur 6. Okay, it is intermetallic, just exactly the vertical line. All right. Okay, so the intermediate phases. Okay, example, copper and zinc. Okay, so it can be alpha. Okay, and no, sorry, the far left and the far right is the terminal phases. So the intermediate solid solution or intermediate phases may be found at other than two composition extreme. Okay, if you look at the previous example, which is this example, there are only terminal phases and the mixture between the two terminal phases. But for the complex phase diagram, okay, you may see a lot of intermediate phases. Okay, so in this example, we have beta, gamma, delta, and epsilon. Okay, so these guys, they are in the form of solid solution. It is not intermetallic. Okay, it is intermediate phase, but not intermetallic compound. They are not intermetallic compound. Okay, they are going to form different crystal structure than either pure copper or pure zinc. Okay, they are different crystal structure. So for copper, okay, in the form of alpha, consists of mainly copper atoms with some zinc atoms in the FCC crystal structure. Okay, so this alpha is still maintaining FCC crystal structure. Okay, so this terminal, okay, terminal phase is mainly zinc with some copper atoms, and it's maintained the zinc crystal structure, which is HCP. Okay, for the alpha FCC, that's originate by the copper. This one is crystal structure for the zinc, because the majority of this phase is contain zinc. Okay, but for the complex phase diagram like this, where you can observe various phases, okay, various intermediate phases. So they change the crystal structure. Okay, for example, the beta phase. Okay, uh, uh, okay, for beta phase, for example, it's contain BCC crystal structure. Okay, it changed in terms of the crystal structure. So this is you need to understand. You can assume that if you have a copper and the majority of percentage of copper up until 40%, for example, okay, or maybe up until 60%, because no, sorry, 60% of copper, you cannot assume it is a having copper. You can assume that if it is majority of alloy contain copper, is have FCC. No, actually they change the crystal structure. Okay, and if the majority of zinc, yes, it can have original HCP structure, but actually intermediate phases is already changed the phase, the crystal structure. Okay, all right. When we discuss on alloy behavior, okay, during cooling from liquid. Okay, for example, let's say this copper containing 40% of zinc. Okay, the melting temperature, of course, above 500, 903. Okay, so let's say at 1000 degrees Celsius, is contain one single phase, which is liquid. Okay, this is a liquid. All right, at temperature 890 degrees Celsius, okay, the solidification begins, and the solid of this alloy at this temperature is the formation of new phase. What phase is it? What phase is it? Excuse me. Hello. At temperature 2, at this point number 2. Okay.
Is it mixture?
The mixture of what?
Beta.
Beta. Which one is beta?
Small.
Small circle. All right. This is solid. Okay. And which is a beta. And the mixture between beta and the liquid. All right. And then after it reduced to point number 3, let's say this point, a temperature of 630 degrees Celsius. Okay, what is the phase? Okay, maybe 809. Okay, I put up here at this point, all you can see is one single phase of beta. Okay, this temperature 2, I assume right above the liquidus line. But at this temperature, where it's completely transformed into beta, right, the microstructure is single phase plus the grain boundary of beta. Okay, you can see the grain like this. Okay, this is beta. Okay, so it is contain only one single phase. But once it cross at 800 degrees Celsius, okay, the diffusion still occur because still high temperature, even though it is 100% solid. But imagine 800 degrees Celsius. So meaning that what happened inside? Okay, there are still atoms moving, and they arrange themselves, diffuse inside the solid to form new phase. Okay, so at point temperature at 100 degrees Celsius, the atoms arrange a new phase form. What is new phase? Okay, basically it will form at the grain boundary. Okay, new phase is the alpha. Okay, alpha, and this is beta. Okay, and it will remains as alpha plus beta, and upon cooling it will rearrange themselves, okay, forming a lamella. This is not really lamella lah, okay, it's just a mixture between alpha and beta, diffuse again from the grain boundary, okay, to the solid beta, okay, at room temperature. Okay, so again same practice when we have a complex phase diagram like this, alpha plus beta, at point temperature here it is alpha plus beta. What are the composition of this phase? Okay, we can use the time line, okay, and we just straight away read at the bottom, okay, where over here is alpha, so the intercept between the time line and the solver's line, this is solver's, okay, because they separate between two phases of solid, okay, solver's line, okay. So we can read this line, so since it is alpha here, so therefore this is a composition of alpha, and this is beta on the right side, so this is the composition of beta, okay. So if we read the composition of alpha, is contain 38 of zinc, because if we read the diagram from the left to right, it is weight percentage of zinc, okay. So let's say this is your alloy containing 40% of zinc, okay. The point at this alloy for the C alpha, it is 38% of zinc, and the remaining composition of the solid is 62. And for beta, you can straight away read from here, it is 44. And then the remaining composition is copper, which is 56%. Okay, and then similarly to the previous example, when we want to measure the fraction of phases, okay, we have alpha plus beta. So how many percent of beta and how many percent of alpha? Okay, the fraction. Okay, we can use the level rule. Okay, where A and beta, A and B length, right? So we know that alpha is here, and beta is here. So beta, we take the length of A divided by total length. So we obtain this value, which is 33.33%. And the rest will be 66.67% is alpha. Okay, the effect on mechanical behavior, alpha brass, okay, copper zinc has FCC, is a structure. So when we talk about FCC, what does it mean? It is more ductile. Remember FCC, ductile. Okay, example of FCC is copper, and zinc have BC, not BCT, SCP, hexagonal cross peg. It is brittle. Okay, right. This is microstructure of alpha brass, where it's contained 20% of zinc. So small amount of zinc, so small amount of HCP structure. So the majority dominated by FCC. So if you have this alloy, you can do deformation process, plastic deformation process. So it has better cold working formability. If you want to change the shape of your materials into whatever the final shape, it's possible to use this kind of alloy. So so now you know the microstructure is related to the mechanical properties and also relate to the process. Okay, beta brass is stronger and harder. Okay, but because of the crystal structure is it is brittle. Okay, because it's contain HCP structure. And this is microstructure of beta brass. They can only be hot work and cast. Okay, what does it mean? Just now we talked about a majority alloy contain copper, and it have FCC, and it have a possible process for co-working. So if you want to, it is it's correlated, the material, the structure, microstructure, and the process, and the type, the properties. Okay, if you have a element of zinc which has a HCP structure, it is brittle. So process is only hot work or cast. Okay, so it's interrelated. Whatever the elements, microstructure relate to properties and relate to the process. So if you want to do co-working process, you may destroy the material because of the brittleness. If you have alloy containing higher percentage of zinc. Okay, so it is still 45 only, but it's still the majority is which is 55%, 55% still copper, but the properties does not allow you to do the co-working process. Okay, so beta brass known as a duplex brass. Okay, the microstructure of alpha beta brass. Okay, the alpha is a lighter color and the brass is darker color. Okay, this alloy is both harder and stronger and has a lower conductivity than alpha brass, and less workable than alpha brass at room temperature. Okay, you cannot easily do any machining process for this alloy. So if you want to make a product from beta alloy, you have to do by casting or by induce a temperature to deform it. Okay, between 50% to 70% of zinc, we have a gamma phase. Okay, so if you have a alloy containing 50 to 70%, you have gamma, and this is the cubic lattice of the gamma. And for example, like this kind of alloy which containing 50% of zinc, okay, gamma is precipitates out of beta brass matrix. Okay, okay, may I know what is phases here? What phase
Sorry.
at this point? What is it? At this point?
Sorry.
I couldn't hear you.
Is it solid, doctor?
Yeah, what solid? What kind of phase? The solid. It is no more
Beta.
liquid. Okay. At this point, exactly this point. This point. 82. What phase?
Beta solid.
Beta. But beta is only here.
Beta plus gamma.
Oh, that's good. Beta plus gamma. Okay, what about this point? This is not beta plus gamma. This point. What about this point? Point B. Point B. What phase? What phase for point B? Point B What is it? Ni salah ni.
Beta prime plus gamma.
Yes, that's right. Beta prime plus gamma. That's good. Okay, what about point C? Point C? C apa C? Delta ni kat sini eh. What is point C? Delta ni kat sini eh. Silap ni. Lari lagi sana. Right. What is C? What is phases present at point C? Nampak tak saya lukis C ni? Ni C. Okay, the composition of zinc is 90%. And the temperature is about 500 degrees Celsius. Okay, point C is temperature equal to 500 degrees Celsius, and the composition for at this point is containing 90% of zinc. So what is the phases at point C?
Solid zinc.
Solid apa? Epsilon E ni. Ni. Plus
Delta.
delta. Okay. No, actually. When we want to determine the phase at this point, it is combining between the phases from the left and the phases from the right. Okay, so now on the left is epsilon. Ataupun awak tak boleh nak sebut E lah kot. Sebut E lah. Okay, symbol tu ni epsilon kan. Plus liquid. Okay, so last time I have already explained how they label the phases inside the phase diagram. Okay, basically is if you have alpha, the next this is the border between left and right. The next phase is alpha plus the next phase. Okay, they label it. Okay, next we give beta, right? And then they got beta. Next will be beta, and then beta plus something else. Okay, because they always mixture like this. You will observe, for example, like if you have a point at alloy that contain 50% of zinc, they will observe it's contain two phases, which is alpha, gamma and beta, gamma and beta. So this is why they come up with this conclusion. Okay, first, if you have single phase, the next will be the mixture between the two single phase. One is alpha, another one is beta. Okay, the next will be the mixture between two single phase, which is, for example, gamma. So that's why they come up with beta plus gamma. Okay, so if you can see here, this is single phase. So this phase is a mixture between alpha plus beta. This is what they observe at this point. Okay, 50% zinc. All right, for the 50% zinc, what they can see is a two different color if they look at the under microscope. And they investigate, they found out one is a single phase of gamma, another one is beta phase. Okay, so in the phase diagram, they have this kind of system. Okay, single, double, single, double, single, double. All right, so now we talk about solid solution. There are another phases which is intermetallic phase. So that's the reason why I corrected this point, okay, which is the delta. Delta here is not located, it is not belong to that point. It is actually at this point. Okay, so the region here is supposed to be delta. Sorry. Okay, the correction here, it is supposed to delta plus liquid, because this is liquid, this region is liquid, this is liquid. Look at this liquid. Okay, so please note this. Okay, ni anak panah dia hilang. Alright. So just now we talk about solid solution. Okay, alpha, beta, gamma. Next is intermetallic compound. Okay, in the phase diagram, intermetallic compounds are represented by lines, not area, because stoichiometry composition is exact. Okay, if you have 30% atoms inside the crystal structure of alloying element, the remaining 70% is exactly at that composition that forming the phase. Okay, what we call intermetallic. For example, magnesium plumbum alloy here, this M value and composition. So can you see not M ni in this daripada soalan exam got dulu. Right. So look at this point. Okay. This label point on this intermetallic. So the intermetallic is known as single phase with specific crystal structure at precise combination. All right, so in this example, it is a magnesium to plumbum. All right, so if you look at this phase diagram, okay, one is single phase alpha, another, the next one is a magnesium single phase, this crystal structure. Okay, single phase of intermetallic. So magnesium to plumbum is a one single phase. Okay, so the between phase, okay, between alpha and this intermetallic, which is represented by vertical line, is the mixture between these two single phase, alpha and magnesium to plumbum. Okay, if you look at this region, it's contain beta, where beta come from this point. Okay, mixed with this vertical line. If you look at this region, it's missing between this vertical line, which is intermetallic, and the liquid. Okay, this region is belong to liquid phase. Okay, if you look at this point, this region, okay, for this region, it is liquid because liquid coming from the left side and plus the intermetallic. Why? Because the intermetallic coming from the right side. Okay, so this is go to this point and liquid go to this point. So that's the reason we got liquid plus magnesium 2 plumbum. Any question? Do you understand? Can you follow?
Yes.
Can
All right. Very good. Okay. So this is terminal phase. It's contain the magnesium rich elements, which is alpha. And this is the beta side. Okay. It's a plumbum rich solid solution. Okay. It is solid solution. It is not intermetallic. So the composition is very depends on the temperature. So you will obtain alpha phase at from 0 until maximum 40%, about 40% at temperature 475 degrees Celsius, about that temperature. Okay, it's a solid solution. The composition is very depends on the solubility. Okay, but magnesium 2 plumbum form when 80% plumbum is mixed with 81% plumbum is mixed with 90% zinc. Okay, where you will get exactly magnesium 2 plumbum, the intermetallic. Okay, so this is the intermetallic microstructure. The cubic structure, we call it, you don't have to memorize it, meaning that, okay, this information is available in the database. You can Google it. But in this example, just want to show it is still cubic structure, but it's contain anti-flow right cubic structure. Okay, so they are different compared to magnesium and also the plumbum crystal structure. So how to integrate phase diagram with intermetallic compound? What happened during solidification? Molten materials containing 81% plumbum and 19% magnesium is it will solidify and forming at one single phase, which is at 650 still in liquid form. And then at 550 degrees Celsius, magnesium plumbum start to form. This is an isothermal process. The solidification will end at the same temperature after liquid transformation to solid, okay, similar to pure metal, okay, because it is contained only one single phase at one temperature. So it is isothermal temperature, because the changes from liquid to solid occur at one single temperature. Okay, what happened during solidification? Molten materials contain 67% plumbum. Okay, at this point. So all right. May I know what is the reaction here? This point.
What are
What
the
is the reaction here? What is the reaction at this point?
Eutectic.
Eutectic. Okay, eutectic temperature, because it is eutectic. Yeah, you will. It is eutectic because it transformed from liquid to two different solid, which is alpha and intermetallic magnesium 2 plumbum. Okay, so upon cooling at this temperature, meaning that above 450 degrees Celsius, you will obtain 100% liquid. Okay, at not 500, sorry, this is 470. Okay, all liquid will transform into two solid, and of course it's contain eutectic composition. Okay, eutectic composition. So imagine it is a lamella, but inside the lamella is contained a layer by layer of alpha and magnesium 2 plumbum. Okay, at 420 degrees Celsius, two phases alloy consists of magnesium rich solid solution and intermetallic compound of plumbum, magnesium 2 plumbum. Okay, so what happened during solidification of molten material containing 74% plumbum? Okay, so this is how you explain the solidification process. Okay, first it is in liquid form, and then at 510 primary magnesium plumbum. Why? Because at this region, this point, this region, okay, the left side is liquid and the right side is magnesium 2 plumbum. Okay, so meaning that from liquid, new phases is the intermetallic magnesium 2 plumbum. Okay, at 490 degrees Celsius, primary magnesium 2 plumbum or the intermetallic Mg2 plumbum get bigger, and the composition of liquid is reaching the eutectic composition. At 470, the remaining liquid will transform, the remaining liquid, only liquid, whatever the solid of a primary Mg2 plumbum that has been formed, it does not transform into other new phase because it's already solid. So what happened at this point is the transformation from solid to into new phases. What phase? It is this phase. Okay, the I'm sorry, not this phase. Into a new phase, which is this phase. Okay, the eutectic structure. Okay, this at this point, it is eutectic structure. Okay, eutectic structure. So eutectic structure basically a lamella structure of two phases. What the lamella structure consists of these two phases, which is alpha and the magnesium 2 beta. Okay. How to interpret phase diagram with intermetallic compound? Okay, the phase diagram can be interpreted by separating the section as shown. Okay, the purple section has alpha phase and magnesium as terminal phases, and the blue section has magnesium plumbum and beta phase as terminal phases. The microstructure formation, okay, first liquid, and then at point 2, it start to form the intermetallic magnesium plumbum. Okay, this is the solid phase, which is in this case the first solid form is Mg2 plumbum, and then this structure will grow larger, and yeah, it will grow larger, and then at room temperature you will observe, okay, remember you have eutectic point here, so the mixture between these two are the involving the eutectic structure. So let's say the primary Mg2 plumbum is formed here, and 250, yeah, 250. So the remaining will be eutectic structure. So eutectic structure is coming from this point, this eutectic point, where what you can see, it is a lamella or lamella alpha plus beta. Sorry. Sorry. Ataupun lamella beta plus Mg2Pb. All right. So similar to the limited or partial solubility system. Okay. Just the difference is this one is expanded into more than 2 solid phase. Okay, which is alpha, beta plus Mg2 plumbum, which is intermetallic. Okay, but it still contain eutectic structure, but in this case it has 2 eutectic structure. Okay, other type of isotomeration. Okay, we have eutected. Eutected is a phase changes reaction of an alloy in which during cooling a single solid phase transform into 2 other solid phases. Okay, for example like this, okay, this one is correct. The delta is inside this region. Okay, example like this point. Okay, what is the transformation during cooling for this alloy? Is contain 75% zinc, about that range. So what is the reaction, the transformation during cooling? Yeah, can you guess the transformation reaction? Nampak lah on. Okay, so the delta, if you cool it down, it will transform into 2 solid phase, which is gamma and epsilon. Okay, so delta upon cooling, cooling, delta will transform into gamma plus epsilon. So it's very simple. Okay, so for alloy with 25% copper and 75% zinc, okay, so if you cool it down, okay, you will have delta single phase. This delta, okay, and then after passing through the isothermal reaction, which is eutectic temperature, okay, this is eutectoid temperature. Okay, since we are going to use open-ended question where you can do the online exam through the open book exam, open book exam, so you can find the information from internet. Sometimes the terms that you use are different from the textbook. Sometimes they use isothermal temperature, sometimes they specific what kind of isothermal reaction. For example, like this, they use eutectic temperature. So you need to get familiar with these terms. Otherwise, you unable to use a correct search keyword. Okay, for example, like this irritated temperature. Why it is irritated temperature? Because there is a irritated reaction happen, and to identify irritated, it's involved the transformation from one solid into two different solid. All right. During this transformation, what happened is at this point there it's transformed into two different structure. Okay, from this point it's a lamella structure of okay, for example, like this, different different. Okay, so lamella, so in this example a lamella between gamma and epsilon, so you can label this is epsilon, no, sorry, okay. The what do you call it, the darker is gamma and the lighter is epsilon. Okay, you get the structure. Okay, another isothermal reaction is perithetic. When we talk about perithetic, it is the three phases reaction, three phases. Okay, during cooling process, two phases, okay, where one of them is liquid, meaning that solid plus liquid, okay, react at single temperature to form a single new solid phase. Okay, for example, like this, okay, at this region, is contain delta plus liquid. So one of them is liquid, and upon cooling, it produces one single phase. Or upon heating, one single phase of solid transform into two different solid, two different phase, which is one of them is liquid. Okay. So for example, this alloy, okay, initially is contain liquid and delta, and after cooling, is forming one single phase, which is epsilon. Okay, so it's happened because of the atoms arrangement, diffusion. Diffusion occur at different temperature. So it's arranged themselves at this temperature. One of the elements are diffused faster to form a new phase, and during the arrangement, it will form a different phases. Okay, different phases is because of the different concentration of copper and zinc inside the phase. So peritectone, this is the transformation of two solid phase in an alloy system, forming a solid new phase, okay, upon cooling. So for example, like just now we talk about solid transform into delta become an epsilon. This one eutecton. Okay, for this case, if you cool it down, okay, you cool it down, you obtain from two solid into one single solid. Okay, so for example, beta plus gamma transform into alpha. Okay, so that's it for four different isothermal reaction. Okay, uh, the intermediate phase are the phase in between the terminal phases. The stoichiometry of the elements in the intermetallic compound should be exact. An eutectic reaction is a reaction when a single phase transforms into other phases, two other phases. Okay. So peritectic reaction is a reaction when two phase, which is solid and liquid, transform into a new solid phase. And peritectic reaction is reaction when two solid phase transform into a single new phase. Okay, I think that's all for this um, lecture. All right. Now, question. Do you have any question?
Doktor, soalan bukan pasal tajuk ni, pasal assignment tu.
Ya.
Ah, kena nanti time test tu kena apa nama reference ke? Kena ada ke?
Kena ada list of reference.
Kena ke?
Oh, tak payahlah. Tak perlu.
Tak perlu ke?
Uh-uh.
Okay lah.
Alright, just now your friend asked about the assignment where you write an essay for the assignment, short assignment 3, right?
Yes.
Okay, for the short assignment 3, your friend asked about whether or not to include the reference list. The answer is no. You don't have to include references. Okay, just write your essay. Okay, to answer the question. Okay. Since no answer, so let me do a test you with short question. Okay, quiz. All right. Let's say we have insolubility system. Okay, insolubility system. Okay, last example I give to you, example on when we add oil and water. Okay, we have oil and water. We try to mix it. It's not soluble. So insolubility system. Okay. So for this system, okay, let's say there's an alloy for that, cadmium and bismuth. Okay, this alloy. So basically, this is the phase diagram for this element. Okay, we have cadmium, bismuth. All right, so this is liquid. So this is the increase of weight percentage of bismuth from left to the right. All right, so now can you guess what is phase in A, B, and C? What is the answer for A, B, and C? Phases for region A, B, and C. Anyone?
Solid.
Solid what? Of course, solid, because liquid only observe above this line. Okay, this is the only liquid that we can observe. A, B, and C, there's no more liquid. Okay, this is temperature versus composition. So what is the phases for region A?
Just alpha.
Oh, sorry. Liquid is supposed to be up until here, liquid. Silap. Okay, so what about A? We still have liquid. This is, okay, let me label this first. Okay, I'm so sorry. This is really confusing. Okay. Okay, let me give a label. This line, liquidus. This is solidus. This is solidus. This is liquidus. So what is the phases in region A?
Liquid plus alpha.
Liquid plus alpha. Okay. What about B?
Liquid
Liquid plus beta.
Liquid plus beta. What about C?
Alpha plus beta.
Alpha plus beta. So how do you get alpha and beta? Where's alpha and beta?
Alpha from cadmium.
Cadmium. So where's the region of alpha? Because just now I explained that when we arrange the faces, it's contain a single faces of A and then B plus A and then B and then B plus C and then C. Single, single, single. This one is mixture between the left and the right. This one is a mixture between the left and the right. So now, what is for A, region A, what is on the left for region A?
Alpha and beta for left side.
Alpha and beta. Or which side? A?
Yes.
For A, okay, for region A, okay, of course, if we have one region in the phase diagram, okay, it's it's a, okay, so what I'm trying to say is region A and B containing liquid. Okay, yes, you're right, liquid. So it's mixed with the one solid inside the region. So the liquid coming from the right, okay, the right side. So the solid, okay, the solid alpha is coming from the left. So what's on the left for this region A? Is it alpha? Where's alpha?
Alpha only like that.
Alpha only. So meaning A is alpha only. Is it? Is that what you mean?
liquid. Alpha and liquid.
Alpha and liquid. So still alpha and liquid. So my question is, where is alpha came from? Patutnya dia campur kiri ke kanan kan? So kiri dia tu apa? Kanan dia liquid. So kiri dia alpha. Mana alpha? Saya tak nampak apa alpha dalam ni. I don't see alpha in this phase diagram. So where you want to put
Liquid
alpha?
plus A.
Liquid plus A. So di salah A.
C plus A.
C plus A. Okay. So salah but okay. So where is A? The A is the region, the level of region.
The left line.
The left line, the vertical line, you mean? This one?
Yes.
So what is the vertical line here?
Alpha.
100%. 100% cadmium.
100% cadmium. So it is cadmium. So vertical line is cadmium. The vertical line here is what? For this
Bismuth.
region. Bismuth. So A is liquid plus cadmium. It is still original compound. It is still original elements, because remember when we talk about intermetallic, it is also vertical line, isn't it? Okay, we go back to our lecture note here. Okay, this vertical line. Look at this vertical line. This vertical line is coming from the left and the right side is liquid. So that's the region. That's the reason this region containing liquid and intermetallic Mg2 plumber. Okay, similarly to this, the concept is similar. Okay, this is what I want to you to understand how we interpret phase diagram. Okay, for this insolubility means that it does not form a one new phase label alpha or beta. No, in this case, there's no such solid solution. It is still original cadmium and bismuth in their own crystal structure. So what about B? What about B? What is the answer for region B?
Liquid plus bismuth.
Yes, liquid plus bismuth. What about C?
Cadmium
Cadmium plus
bismuth.
bismuth.
plus bismuth.
Yes, very good. So just see, it is the same concept. Okay. So if you have this point, it is intermetallic of lamellar structure between, let's say you have this alloy. Okay, you will have lamellar structure, lamellar layer per layer lah. So this one is maybe cadmium, and this darker line is bismuth. Okay, so it is eutectic. Right. Okay, sama saja. And again, this is vertical line, pure metal, because it is 100% bismuth. Okay. Nampak pula I. Right. I think that's all for this lecture. If you have, do you have any other question?
Doctor,
Do you have? Yes.
I want to ask, it will only have lamellar structure on the eutectic line, is it? It will only have a lamellar structure on the eutectic
Yes.
line, is it? Is it?
Yes.
Okay.
This one. It is eutectic alloy of bismuth plus cadmium. So if you have about 80% bismuth, all right. So what happened here is forming primary bismuth, because here we have bismuth plus liquid. So at this point we have, let's say this is bismuth. Okay, bismuth. And this is liquid. So at this point, the bismuth has grown larger. This is bismuth, and this is a lamellar structure. I'm sorry for the poor sketch. Like this. Okay, this is primary bismuth and the lamella. So if you look at the composition, let's say this is the boundary for the lamellar structure. So it is whatever your alloy here at this region, hypereutectic, is contain a mixing from the left, which is the intermetallic line, and the right is a pure bismuth. So you can have this kind of microstructure. Okay, hypo and hyper. All right. Once again, if we have this kind of structure, okay, whether it is insoluble or partially or limited solubility, okay, you have it's a left and right. So now this is eutectic. So whatever left is hypo eutectic, whatever higher this region is hyper. As long as your alloy passing through this isothermal temperature, this horizontal line, this eutectic temperature. Okay, if the composition of your alloy within these limits, okay, in this case it is 100%, because from 0 to 100% of bismuth if you add bismuth into cadmium. Okay, so the mixture in this region, of course, cadmium plus bismuth. But if you're focusing on only hyper, it is actually a mixture between this vertical line and this vertical line. Okay, so your hyper alloy containing left is lamella, right is bismuth. Okay, bismuth on the right, lamella on the left. This is lamella or eutectic structure. This is bismuth. Sorry. Tulis lagi. Lamella. Okay. So this is applicable for the rest of the system. Partially limited or even complex structure. Okay. Any other question?
No, doctor.
Okay. If no other question, I think that's all for today. And once again, I will share the attendance for today. You can scan your attendance. Okay. So please scan your attendance and you may leave